Hello students. Today we are going to discuss some concepts of physics which are very crucial to understand not only physics but also some daily life concepts. But sadly we will not discuss deep into concepts and we will try to discuss only some numericals that we have. But always remember the concept of work, energy and power that we are discussing here. So first thing, what is work? Work is something whenever we apply force, and that force amounts to something like that creates some kind of effect, then we can say that work has been done. Second, what is energy? So energy is nothing but it's the ability to complete that work, to make that change using that force. So, and what is power? So in general language, power is, we use power as something about forceful, but here we completely distinguish the two terms, force and power. Force is the ability to make a difference, that's force, or say force is the ability to create a change in momentum. But power is something different. Power is the rate at which a change is made, or the rate at which energy is delivered, or the rate at which work is done. So you can say that whenever we apply force, work is done considering the effect is there. Like if we have applied a force to a car and it has moved to some distance, there's definitely a force done here. On force has done some work there, and energy is spent in that work, because some energy has been applied, some energy has been put into work, and therefore we can see or we can visualize the effects. And power, so if we are pushing a car, or if we are exerting a force and we are uh, doing some work, the same work can be done in time t, the same work can be done in time t dash, means the work can be done in different times, so the rate at which work is done can differ, and that rate is power, rate of doing work. So we'll discuss some concepts, some questions based on these concepts and try to solve it together. So here, sorry about the question that has been, I'll try to explain everything, but some parts have been pixelated, so I'll try to write them down. So in these questions, in this question we are discussing some concept that involves the relation of work and energy obviously. So let's read it. Two particles of masses m1 and 2 move with initial velocities u1 and u2. So obviously the initial velocity would be initial kinetic energy of these two masses would be something like let me change color. Now for this would be half m1 u1 square, as you can recall the formula for kinetic energy, and this one would be half m2 u2 square. And on collision, one of the particles gets excited to a higher level after absorbing energy E if the final velocities of the particles be v1 and v2, then we must have, so a collision has taken place and at the same time one of the particles has absorbed energy. So we are doing conservation of energy, right? So before and after situation, In first situation, two are colliding and one is getting some energy from outside. So obviously the total final energy would be total initial energy plus the extra energy that has come to the one of the particles, and one of the particles, we don't know which particle. So obviously we will relate them as kinetic energy initial is equal to kinetic energy final, but we have one twist here, that is one extra energy here is getting added. So this would be our equation which we need to find and select the options from here. So first thing here, we see that this is dimensionally incorrect. We can simply strike this option out. A is not a correct answer. Now second one, yes, dimensionally right. This one is dimensionally right. This two, this two. So we can say that yes, this has same dimension. Let's check C, same dimension, okay. Let's see. So rest three options are dimensionally right. We can move to check which one is the right answer. So if you see, option B and option D are nothing but the same concepts. Like if you remove E from here and put on the right side, we would be getting same equation as in B. So B and D are identical solution. We can eliminate these two, but don't consider that. Simply say that let's check. One of the particles gets excited to a higher level. That means in the collision, I have made a mistake here. Right, something. Yeah. One of the particles have taken energy from that collision. Means earlier the two particle system had some energy in form of kinetic energy. In the collision, one part of that energy E has been given to one of the particles, which took it to a higher level of excitation. Might not be anything related to speed. It might be something related to the position, to some kind of different form of energy. So we are considering that that energy is not kinetic energy anymore. So we would say that has been converted to some other forms of energy. So we will say that minus E. Initial kinetic energy has been compromised by this value E, and the final kinetic energy is smaller than that, and that is given by our answer C. So C would be the right answer. You see the initial kinetic energy here and the final kinetic energy here, and we know that this much energy has been lost. So initial minus lost energy is equal to the final energy. Let's move on to the next question and see what we have. So a block of mass 10 kg moving in x direction with a constant speed of 10 meter per second is subjected to a retarding force F equals to 0.1x joule per meter during its travel from 0 to 20 meter to 30 meter. Its final kinetic energy will be. It's a very nice question which involves a little bit of integral calculus, because you will be having a variable force. It can, however, be dealt with a different way of solving. Let's try work it out. So what variables, what given forms we have? We have 10 kg mass. Our mass is 10 kg. Moving in x direction, so this is something mass has started from point 0, and it is moving in x direction here, like this, and it's subjected to a retarding force of 0.x joule per meter during its travel from 20 to 30 meter. So let's say the force started from here, which is 20 meter, and at 30 meter the force has been removed. During its travel from 20 meter to 30 meter, its final kinetic energy will be. So kinetic energy final is equal to kinetic energy initial subtracted by or added with the work done. So a work is done on this block of mass 10 kg, but it's not towards the say to make it move faster, but to make it move slower. That is a retarding force here. So that means our work would be a negative quantity here. So first let's find out what is that work. So let's memorize what we have here. Our force is 0.1x. So let's try and work it out. So we have this situation from 20 to 30 meter, that force is acting on the mass. So let's say this is the path, and we are considering these two: kinetic energy initial and kinetic energy final. So don't confuse with the graph here. This is not a graph, this is just the direction of motion, being the x direction and y direction. I'm just showing it that the body is moving from in the x direction from 20 to 30. We are experiencing a force F, which is acting in negative x direction. Why in negative x direction? Because it is a retarding force, it is slowing our mass down. So the force here, what would be the quantity of force here? 0.1x, that means 2 Newton. And what would be the force here? 0.1x again, that would be 3 Newton. Let's check back our question. It's 0.1x joule per meter, and to avoid the confusion here, joule per meter is nothing but Newton, because joule is defined as Newton meter. A unit, SI unit of energy, joule, is Newton meter, so Newton is nothing but joule per meter. So using that thing here, and we know that it has the force is being exacted from 20 meter to 30 meter. So let's go on and solve it. So the work done, let's say we are talking about this distance here. So we are considering this distance. Let's see the color. Let's say this distance is dx, and it is x from here. At distance x from the 20 meter mark, we are considering a distance traveled dx. So at this is a very small distance, we can consider that the force would be constant throughout. So the force acting here, 0.1 1x, and what is the value of x here? 20 plus x. So 20 plus x into 0.1, we could simply say that divides by, right? 2 Newton plus x by 10 Newton. And we know that here we'll be getting 3 Newton. So the work done is force time displacement. So if in this distance the work done by that force would be force times dx, that is this force 2 plus x by 10 into dx. And this is what the total work would be if we integrate this whole expression for the whole journey, for the whole expense for which work is being exerted, and the work is exerting from 20 meter to 30 meter. So our lower limit is 20 and upper limit is 30 meters. We'll try to integrate it. This comes out as 2x plus x square by 20. Applying the integral, okay, the limit would be 40 to 20. What we are getting? We are getting 20 plus 500 by 20. So dividing by this, we are getting 25 here. So our total force that total work that has been done is 45 joule. And you know that this work is negative because the force already has been negative. So if we put a negative mark here, it will come up to a negative 4. So we have minus 45 joule that has been worked here. So let's come back to here. Our initial kinetic energy is what's our initial kinetic energy? It's 10 meter per second square meter. So half mv square mvi square, because initial velocity we are considering vi. And what is the work? We just calculated our work is minus 45 joule. If we calculate our half mv square, half m, that means half of 10 kg times 10 meter per second, the whole square. So 5 into 10 square, that is 500 joule minus 45 joule. Do we have a right answer among the choices? Yes. I think we don't have. One of the right choices missing. So this would be 455 joule. Don't worry about the right answer, wrong answer. None of the answers is right. The correct answer would be 455. So let's write here. This would be the right answer if considering I have just changed the answer here. 475. We'll be looking at another question. I hope this doesn't involve that much of integral. However, that integral question could have been dealt in other ways. We could discuss that in other classes also. So the question here is a body of mass 4m. So we are considering 4m, don't confuse it with 4 meter. The mass is 4m, is lying in xy plane at rest. It suddenly explodes into 3 pieces. 2 pieces each of mass m move perpendicular to each other with equal speed v the total kinetic energy generated due to explosion is. So this is slightly complicated in other way because we have angles involving here. So body of mass n is lying in xy plane. So let's say this is the xy plane. And it suddenly explodes into three pieces. Earlier say it's a 4m mass and 2 of mass, say m and m. This would be 2m, the total mass. Move perpendicular to each other with equal speed v. So let's say this moves in this direction, this moves in this direction, being perpendicular to each other. With what? With equal speed, so both are v. The total kinetic energy generated due to explosion is. So do we have the total, all the ingredients here to make our recipe? Here m, v, this m, also v, but we don't know the velocity of this part here, that is the 2m, obviously, because 4m is breaking into three parts, 2 m and m, the last part would be 2m. This must have a velocity somewhere here to accommodate the which we call as law of conservation of momentum. So this part has to equate the total momentum acquired by these parts here. So suppose this has a momentum p in this direction, this would have a momentum p in exactly other direction. So let's just find out the total momentum in this direction. So the sum of these two, the sum of these two would be something like this. Using parallelogram theorem, we would simply say that the total, both of these momentums are mv and mv at perpendicular to each other. So the resultant of these would be making 45 degrees from both, and since this is oblique, making two arms of a square, we can simply say that the resultant would be square root mv, the total momentum of these two, total, or say the resultant momentum. So what would be the resultant momentum of this 2m particle, or the 2m part of this 4m mass? That would also be square root 2 in this direction, opposite to this one. So if we find the kinetic energy using this, so first it has 2m square root 2 mv momentum, so its speed would be divided by 2m, the mass of this part. So velocity that comes out is v divided by square root 2. So the kinetic energy would be half, mass is 2m, times velocity square, so v by square root 2 the whole square, that would be v square by 2. Crossing out, we would be getting half mv square, right? Now carry out the calculation, see this mass, these two pieces, all with the speed v, half mv square plus half mv square, and this one again half mv square. So we have three pieces flying with kinetic energy of half mv square. We are getting 3 times half mv square, that would be 3 by 2 mv square. I would like to know if you have any doubt. If you don't have, we can move on. Okay, so this question again related to energy, and let's read it out. A body of mass m taken from the Earth's surface to the height equal to the twice the radius r of the Earth, the change in potential energy of the body will be. So let's try this together. This is our Earth, radius being r. So body has been taken from here. This would be the body, and it has been taken to a distance, suppose, let's say this is raised to twice the radius, equal to twice the radius. So obviously it has reached such that the height is 2r. So we need to find out what is the change in potential energy. So earlier the potential energy would be something, we know the change in potential energy is calculated simply by mgh, right? Where h is the height attained. So what would be the value of h here? That would be 2r, right? So mg times 2r, and our answer would be 2mgr, right? 2mgr. It has been written in mg2r, something like that. This should be here. So this would be right answer. Am I right? I am missing any kind of response from you, but no, this is not the right way, because the force that is responsible for deciding the potential energy of this mass is not constant. Whenever we are moving up in the direction away from Earth, the gravitational force is decreasing. That's why we cannot assume that our h would be simply put as 2r, because there is not a very small change in radius or very small change in altitude. This is a quite considerable change, and even larger than the radius of Earth. So we cannot use this. So all this work here is wrong. We would have to consider the gravitational force first. So let's first go on and first see what is the potential energy of this object, this mass. Let's consider the mass as m. The potential energy, and consider the mass of Earth is capital M. The potential energy is G m m by r. Negative because we consider two mass system to have zero potential energy when they are far apart, and whenever they come close to each other, their potential energy decreases. So this is negative. Whenever they go up, the potential energy increases. So sorry, whenever they go apart from each other. So you see that if I'm moving up in the air, my potential energy increases. That means if I'm at the infinite distance from the Earth, my potential energy would be at highest level. So definitely if this thing is considered as 0, the highest level, obviously 2 point systems potential energy is always negative. So let's consider what is the final after the attaining a height of 2r. After attaining a height of 2r, the radius is now 3r, right? R plus 2r. So our final potential energy is equal to minus gmm by 3. So our work is done, initial and final. Subtract them, initial minus final, you will get the change, and that would be 2 by 3 gmm by r. Now, do we have any option that we have capital G and mm, that is that some that stands for the mass of Earth? No, we don't have. We have the values in small g. So we have to convert out this form into small g. We know that the acceleration g is given as the force of attraction divided by the mass of Earth. So g m m by r square. So if we are considering this thing here, gm r by r square, or say this would be the radius of Earth, so this capital R. So if we are considering only gm by r, only this thing, we would be getting gm by r equals to r times g. That will give us 2 by 3 r g m. We can always rearrange this thing. So mrg would be here, mgr, 2 by 3 mgr. This would be the radius. Okay, let's move on to the next question, and always try not to fall into the mistakes that I have shown here, going from 0 height to a height of 2r and using the formula mgh for the change in potential energy. Okay, in such cases, whenever the change in altitude is considerable as compared to the radius of Earth, we would not use the formula mgh. We will go into the basic formula of gravitational potential energy. Okay, moving to our next question. What we have, let's see. We have a question with light energy. Okay, a 200-watt sodium street lamp emits yellow light of wavelength 0.6. Let me change it. This should be micrometer. Okay, 0.6 micrometer, assuming it to be 25% efficient in converting electrical energy to light. The number of photons of yellow light it emits per second is. So we need to consider these things here. 200-watt sodium street. Whenever something is written on a apparatus, on a machine, that it is 200 watt, it is 1000-watt machine, that means its input is this much. So it is taking 200-watt power to get illuminated, and out of that 25% is being converted into light. So let's find out the light energy it is emitting per second. First, the light energy. Our energy is equal to power times T. Our power is 200 watt and we are considering 1 second. So 200 watt into 1 second, we will be getting 200 joule. But efficiency is only 25%. So obviously the energy in form of light would be 25% of 200 joule here, and that would be 1/4 of this, 50 joule. And now we have to find the number of photons of yellow light it emits per second. Yes. So how many photons are there whose total energy is 50 joules? That's what we have to find out. So first thing, the wavelength is 0.6 micrometer. You can use this thing. To move fast forward with this question, let's try to sum up quickly. So energy associated with any wavelength is equal to h nu, or h frequency, or we have been given the lambda part, that is the wavelength. So we would say hc by lambda. Using this, we will calculate the energy per photon, and suppose this energy is E dash. So number of photon in this much energy would be simply 50 joule divided by E dash. So all you have to remember is the values that can be used for converting the wavelength into the energy of photon, and then divide that energy with the incident energy per second, at least for this type of question. Moving to the next question, we have two cities which are 150 kilometer apart. Electric power is sent from one city to another through copper wires. The fall of potential per kilometer is 8 volt, and the average resistance per kilometer is 8 volt. Okay. There's a mistake. I just corrected 8 ohm, and the average resistance this part is redundant. My mistake, sorry about that. So the fall of potential per kilometer is 8 volt, and the average resistance per kilometer is 0.5 ohm. The power loss in the wire is, so the total distance is 150 kilometer. We know the resistance per kilometer is 0.5 ohm. So total resistance of the wire is 150 times 0.5 ohm. That would be 50 ohm. This is electrical energy, so all we are using is the formula from electrical power loss or electrical power in a conductor. So 75 ohm, and the potential drop is 8 volt. So 1 kilometer के लिए potential difference 8 volt है. 150 kilometer, the potential drop delta V would be, what we are writing delta V? Okay, we can write it. Delta V is 150 times 8 volt. That would be 1200 volts. So power loss, we are finding power loss. Power is equal to V square by R, that is the square of the potential difference, or the difference in the square of the potential difference, the initial potential to the final potential, and R being the resistance. We have both the quantities here. We can simply put and find the answer. To 1200 volt square divided by 75, we would be getting would be calculation here. This is around 1200 into 16 joule. That would be 150, 200. That would be 15,200 joule. Sorry, I'm again. So this is joule per second. That is 15,200 watts of water, watts of power is being destroyed or being wasted in this long. So that's why you might know that whenever a power source is different from a city, is quite distant from a city, it is quite costly to supply power from that point. That is why it is beneficial to keep the power sources close to the source, close to the places where the electricity is being supplied. So this again we'll try and wrap up with this question, but let's consider this is a question where you need to analyze some parts. Let's read it together. Two similar springs P and Q have a spring constant. So we are considering spring energy, spring potential energy here. Spring constants Kp and Kq such that Kp is greater than Kq. They are stretched first by the same amount, case A, and then by the same force, case B. The work done by the spring Wp and Wq are related as in the case A and case B respectively. Okay, we only have to compare systems and find our answer. So in the first case, case A, they have been stretched by the same amount. So what could be the stretching? So let's say P and Q both are stretched for X meter. The work done here is spring potential energy formula, half kx square, half kp x square, the same half kq x square. So comparing these two, this energy of P and energy of Q means the spring potential energy of P and Q in case 1. Case 1 or say case A as written here. So case A, we are extending both to the same amount, that is same distance, x meter. So Kp, we are getting the spring potential energy as half Kp x square and spring potential energy of Q as half Kq x square. We know that Kp is greater than Kq. So this part here, Kpx square would be greater than Kqx square. So Ep, energy of P, would be greater than energy of Q. And we are considering the work done. Obviously, in compressing or extending, the work done is same as the energy acquired by the springs. So that's why Wp would be greater than Wq here, right? Now we are considering the second case. In fact, we don't need to consider the second case because we have only one choice where we are getting Wp by W is greater than Wq, but let's go and find out the second case also. So second case, case B, says that both have been compressed, they have been stretched by the same force. So same force is applied, that means the stretching of first P would be F by Kp, and stretching of Q is F by Kq, where both F is here are the same things. So considering these two, we would be getting our work done here as half Kp into F square by Kp square, and half Kq F square by Kq square. That means we would be getting half of F square by Kp and half of F square by Kq. In this case, Kp is in denominator, so something which have a bigger denominator is a smaller fraction, right? So this value, that means energy of P is smaller in case of energy of Q. So that's why WQ is greater. So our answer is C, which is giving, if the stretching is same in both the springs, then the work done in the spring which has greater spring constant would be greater. But if the force has been same in both the springs, then the work done in the spring which has smaller spring constant would be greater. So that's our answer. And I think, permitting our time, we all have that we can cover up. Thank you for staying with me. That's all for today. We'll meet soon.